So thanks everyone for joining this session where we're going to discuss test-driven development. I'll just put a link there in the chat. So this is a link to the GitHub page where you can find all the material from this presentation. So yeah, my name is Anton Sundqvist and I'm based in Finland here on the Finnish West Coast. Let's see if we can get this one visible as well. Yeah, so I'm an avid proponent of test-driven development, and I've been talking about it a lot at different occasions. Most recently at the GDevCon in Amsterdam this year, where I had a presentation which was more focused on how to do test-driven development with hardware, or when hardware is involved. So I've also worked on the tooling to make the workflow better for test drivers. So I've released an open source unit testing framework, which is very fast and has a very nice workflow. So if you haven't seen it, you should go check it out. It's also open source and free. So go have a look at it if you're interested. Yeah, so let's see if we can get this one there. Yeah, so just to give you an introduction to what I'm gonna be talking about today. So as I mentioned, we're gonna be looking at test-driven development, but in the form of an example where we solve a CLD exam, where I will walk you through the solution of the exam using the test-driven development, and then we're gonna have a look at the design which comes out of that and how test driving it actually impacts the design. So it's the ATM CLD exam example which we're going to look at. We're going to discuss the design process, and then analyze it a bit and draw some conclusions from that. The purpose is not really to help you get through your certification, even if you wanted to do the CLD as Matthew proposed here using TDD. I don't think it would be very easy because you don't have the tooling, I guess, natively in LabVIEW. You might have the NI unit testing framework, which could possibly be used, but the purpose of this presentation is not that. The purpose is to, by example, show some test-driven development. And the reason I wanted to do this is really because if you haven't done test-driven development, it's kind of difficult to understand why it impacts the design and why it is a good idea to do. So this is the purpose here, to try to explain really why does it improve the design as I'm saying that it does. So it's going to be pretty much a sales pitch for test-driven development. But before we go on with that, let's have a look at a rough or some kind of attempt of a definition of software quality. I like to use this because it kind of tells you what I mean when I say that something gets better. So let's look at what, in a simple case, what we might care about when we talk about software quality. On the one hand, we care that the software does what the user expects it to do. And on the other hand, we want it to be easy to change. So what I mean when I say that something gets better is that it does more of what the user expects and it gets easier to change, or at least one of these improves. So of course, the next question then is, how can we produce high quality code at a high pace? And this is what we're getting at with this presentation. And for me, at least, the only thing that has worked so far is to try to minimize the mess that you make while developing. So the only way to go fast is to not make a mess while going. And to try to give some illustration of what I mean by this is that this is typically what a software development process or system development process might look like. In the start, you accelerate, you're pretty fast at adding more features, but as the size of the application grows, it gets more and more difficult to add features. And each time you want to add something or change something, you need to make sure that anything that you have added before doesn't break. So what we can do is we can use automated tests to prove that our system is still working, or prove is maybe the wrong word here. I'm not trying to prove that it works. It's more about getting confidence that the system still works, increasing my own confidence as a developer, not to prove to a potential customer. So the idea here is that by improving the internal quality of the system, we can keep adding features to the system over a longer time at a higher pace. And the interesting question here then is, when does this start to pay off? Where is this break-even point? And my argument that I try to make is that this is actually measured in hours and not weeks or days. It's pretty fast. And I hope to demonstrate this through this example as well, as a CLD exam is something that should be completed in a few hours. Cool. So before we go into it, I want to give you a background to what test-driven development means. So for those that are new to the concept, I'll try to explain it for you. So the main idea in test-driven development is that we drive our development with tests, and that means that we create a test before we write any production code. So before we have anything to test, we do write the test, right? So that's what we start with. After we have written the test, one test, not all of the tests, just one at a time. Then we go on to develop a code which make that specific test pass, and we run all the other tests to make sure that we haven't broken anything while doing so. So we keep doing this, and so we have this add test, make it pass, and then we refactor. And while we refactor and work with the code, we make sure that the tests stay green, that we don't break anything while doing these changes. So we talk about this kind of red-green refactor cycle. There's a question about the PDF. The PDF is available at GitHub. If you go under the presentations folder, you can download it from there. So yeah, the red-green refactor cycle. So red means that the test is failing, green is making it pass, and here we might take shortcuts. We just want to make sure that we get it to pass, and when we have gotten it to pass, then we can change what we have made to clean it up and make it more nice to work with. So, and that's because we have this test which we have seen that failed in the beginning. We know that it actually proves something. It shows that something has changed, that something has started to work. So we know that the test is actually testing something. And importantly here, the cycle time should be very, very short, order of minutes. And for that reason, it's very important to have good tooling, which allows us to run the tests in a matter of seconds. So running the tests should be very, very fast, so that we do it often. So yeah, add a final comment here is that writing the tests is not separate activity from development. It's a deeply intertwined piece of the development process. And I alluded to this already a bit, but why should we bother with doing test-driven development? Because the thing is that as we start with writing a test, we actually have more chores to do. We have more tasks on our list, and it's not like we are not busy from before. So so to give you some kind of motivation to why we might want to bother with this, is first it improves the designs, and this is what I'm going to show you later. The idea of having self-testing code is very appealing because you can, in a matter of seconds, you can show that your code works to yourself. So not to the customers, that's not the purpose here. We want to be able to prove to ourselves that the code is still working as we intended it to. And this in turn leads to less stress because we don't need to be afraid of making changes in the code. We can always have the scaffolding in place which shows that the code is still working. So it's a very nice way of working, in my opinion. And the last point I want to make here is that the tests act as documentation for the code. So we get these small examples of how the modules that we develop, the code modules, are supposed to be used and how they're supposed to work, and when they're not supposed to work if we test for error cases, for example. So this is very nice documentation for a developer then who picks up the code. He can start by checking it out, running the test suite, see that everything passes, and then can start looking at the tests for the specific piece of functionality which you are about to develop. And this is good not only when you work with someone else's code, but also if you work with your own code from a couple of months or even weeks back. It's good to have these tests to show you what we're about to do. So I use these terms test-driven development and test-driven design interchangeably a bit, but what I really mean by test-driven design, so let's talk about test-driven design a bit. And by this I mean the design which falls out of this kind of process. And I already claimed that this improves the design, but to understand this a bit, let's try to understand what makes code testable. And if your code is to be testable, that is, you can hook it up in some kind of fixture, you can test it in isolation, and you can decide if it works or not. Sorry. So first, we need to have the code loosely coupled to the rest of the system. That means that we can run tests without pulling in the whole of the world or the rest of the system into our tests. So we can test the code in isolation because it's loosely coupled to the environment or the context in which it runs. The APIs should be clean and easy to understand, because that makes the process of writing the tests and reading them easier. Dependencies needs to be managed for the same reason as the argument for the loose coupling stuff. And the responsibility of the code module we are about to test should be clear, because else writing the tests will be very difficult, because we are testing a lot of different things. And typically when we write automated tests, we want to test one thing at a time. So the responsibility of the module needs to be clear, and it needs to be highly cohesive, if we want to say that. And finally, side effects are typically nasty to test, and side effects is anything that's not a direct output of our VI, so anything that's not a indicator. So we want to limit that as much as possible, because it makes the testing, if you want to have the code testable. And then the question becomes, what if we start by writing the test? Well, of course, that would mean that we more or less get all of these traits for free, because if we start with writing the test, we don't want to make our lives difficult. We want to make writing the test as simple as possible, which means that we will, if we do it well, at least we will get these benefits out of it. So this is kind of motivation, and of course it's not just a one-step solution to all the problems. There is skill, and you need to practice and develop. But my point here is really that it helps, and it pulls in the right direction. So this was a bit of background to test-driven development. So let's now dive into this fun part of the presentation. Let's have a look at the ATM CLD example. So if you have practiced for a CLD, you might have solved this yourself. I know that I did a few years back when I practiced for my CLD. And it's quite a simple application. It simulates an automatic teller machine, or ATM, where you are supposed to be able to withdraw or deposit money, and you should be able to check the balance on your account. Yeah, it has this kind of front panel which you get with the instructions. The block diagram is empty at the start of the exercise. And then you should implement the different states, like this one, where we insert the card. Then we simulate a account number by entering an input into the field here, pressing enter. And then it checks with the database, which in the exercise is just a flat file. But it checks that the account is valid, and then you can start doing stuff like checking the balance of the account, or depositing, withdrawing. So this is what it looks like where you deposit. You first go to the deposit state, then you select how much you should deposit using the input, which simulates giving money to the machine, I guess, and enter then transitions. And similarly withdraw, and of course it should check that there is funds on the account from which you are about to withdraw. And you're supposed to be able to check the balance, and there's a whole lot of detail here of how this is supposed to work, and everything is laid out to a very high level of detail in these specifications. Cool. So let's first do a quick reality check here. Could this really be something which we would stumble upon in the real world? And could this be a real application? And I would say that it's not that far off. So we have some kind of model of what an ATM does in the background, which allows us to deposit, to withdraw, to check the balance, for example. And this should interact with a database. In this case, it's just a flat file, but why not for the purpose of the exercise? And then we have some kind of presentation layer, which is now a front panel of a VI, but it could as well be real hardware, and there's nothing stopping us, unless our solution is very tightly coupled to the VI, of course. But if we are loosely coupled to the main VI, then we could, of course, hook it up to any hardware we would like. So the requirements then, could this be real requirements? My personal opinion is that probably not, or I have never seen real requirements that are this detailed. And yeah, if you were able to write the requirements with this level of detail, then you might as well write the application yourself, because it's more or less programming by wire, which LabVIEW tend to be. So yeah, the hardware already mentioned, we could swap it out if we had have a good solution. And yeah, but of course it's still a toy example, and it doesn't really make sense to show you any real big real world example, because we only have 45 minutes. So I think the scope of this exercise is very well suited for a 45-minute presentation. And yeah, as I mentioned, you could not really solve the CLD this way, because you don't have the tooling during the exam. So let's get going. As I mentioned, when we work with test-driven development, what we do is we start with a test. We start writing a test for the code which we are about to do. So what I did here when I started working on this, I opened the requirements. I look at the first requirement, and immediately we get into the problem, because here we should test the user interface, or we are about to develop. So ergo, we should test the user interface. We should test that the buttons are disabled when the application starts. And there was a presentation earlier this morning on how to use SLL drone, I think, to test through the user interface. In general, I would not recommend testing much through the user interface, because it tends to be very flaky and very sensitive to changes. For example, if you change the control name or so, you could break your tests. So instead, I tend to decouple my application as much as possible from the user interface, and instead just have the UI logic so simple that it just calls API methods, and then it needs very little testing, and that I can do by hand. Of course, if we have something that a lot of users will use, then it's worth investing in testing it properly. But for my typical one-off test systems, it's typically enough. So let's look at what I mean by decoupling from the user interface. And yeah, there's one rule really that I have for doing test-driven development. And the rule says that when something is difficult to test, we get rid of the stuff which makes testing difficult. And in this case, it's the user interface which is difficult to test. So we get rid of that and test the underlying logic. And what I came up with here is what I call a view model. So I make a model of the view. The view is the UI, and I can place my logic in that class in this case. So the solution will be class-based, object-oriented, but I don't really use any dynamic dispatch or even a lot of access scope to do something object-oriented like. So you should be able to follow it even if you have never seen an object before, just regard it as a cluster. So yeah, let's have a look at the view model, which I started with here. So I realized that I will need to have some kind of class, in this case, containing what would be called the business logic of the application. So this would be the ATM controller, which would handle all the different tasks that this application has. And then I have the view model, which it knows about the controller through the state of the controller. So depending on the state of the controller, we want to put the view in different states as well. We want to update the controls of the view. And that's the purpose of the view model, to handle that logic and to do it in a way so that we can test it. So I started writing it like this. I have a constructor, it's just an empty VI for now. And then I have a VI which basically maps a control. In this case, the enter is the control, and the ATM state is then the state for which we want to know what state the enter control should be in. So this could quite easily be implemented. You could probably guess how the block diagram look here. And this is just a test case. The method or the VI on the right is just the test method, which asserts that the output of this VI is now disabled and read out enum. But I realized that this would work, and it's very functional and nice. It's gonna be a lot of work just to wire this up to the front panel. So I decided to do a more pragmatic solution. So I changed my implementation to this. I create my view model, then I register a control by passing in the reference to the control and saying that this is a reference to the enter control. Now I have in my test, I have a test control here, which I use as a dummy control just for the purpose of testing. And then I can check that when I call the update enable state VI of this view model class, then the enter control goes into the disable and grayed out state using a property node. And my idea is that when I later then integrate this into the main VI, I can just loop over all the controls and indicators on the front panel and just register them programmatically with the view model. So that would simplify my life a bit later on. So that's why I decided to change to this. A drawback here is that we have a side effect. So when we call the update enable state, we have a side effect that the enable state of the control changes. I think it's a pragmatic decision, and it's not that bad, to be honest. But also using the references will slow down the test a bit, but it was not really an issue here. So going on, started to write tests for the view model. We had the message, which is to be displayed on the ATM display. This looked like this when we start the ATM. So we can write a test, creating a view model, and then calling the get ATM message VI on this view model, and then we get the ATM message, which should look like this. So the tests tend to be very simple. They look like this here. So for example, when we have a verification failed, we should get another message. And this is actually pretty nice that they are so simple, because that makes it easier for us to keep everything in the head at the same time. So we can just focus on one specific behavior at a time, and we don't need to think about the whole system or all of the other things around it. So we write a lot of these small tests to test every single function or feature that we care about. And yeah, we also have a button which should change the text depending on the state of the controller in this solution. So when we are in the insert card state here, we should have the Boolean text of the control saying card inserted. So you can probably, by reading the specs, guess that how the rest of the tests would look for this view model. But at this point, I came to the controller, or came to the requirements for the controller, and I started working on this one. And I created a class, I created a constructor for the class, and I started to write tests like this. So I have to tell the controller that we had inserted a card in some way, and I do this by calling this VI card inserted. This I imagine I can later then wire up to the case on the front panel, which would be pressed when the card is, which would be activated when the card inserted button is pressed. And then I expect my controller to be in the card inserted state after this. We can also go on with verifying the user after we have inserted the card. So let's say that the verification fails, then we should get into the verification failed state. And if the verification passes, we should get into the verification succeeded state. So this is what the API starts to look like as we add one behavior at a time. So now we have two classes. Let's add a third one because we pretty soon start to get requirements about the database. And as I mentioned, the database is just a flat file. So for the testing, we can just use a file which I use a relative path to. It's typically a good idea to not use absolute paths when writing tests because we want the tests to be able to run on any machine, not just your own. So typically, over here I used the path of the class and I placed the text file in the same directory as the class. This is now the test case class then testing this database. So we can create we have a constructor for the database. We call verify with a parameter. This parameter, it should probably say on the label here, but this is actually the account number that we want to verify according to the specifications here. And we also want to check that if we enter some account that's not in the database, then we fail the verification. So now we are able to verify the account based on the account number, and we have the API methods for calling that we need to call the controller when we have verified this. We have the view model, which is implemented so far as we need it for now. So at this point, it felt to me at least that, yeah, I need to start putting everything together so that I can see how it fits together and try to discover any mistake I made. So I started working on the main VI, which I hadn't touched until this point. And I wired it up like this. So on the top here, we have the database, which gets the file path here from the main VI. And on the lower here, the yellow one, it's the view model. We create it, and then here we register the controls from this VI. So this is what I mentioned earlier. We just iterate over all controls from the main VI and register them with the view model. And then we can do all the updating from within these view model methods. So the purple one here is then the controller, which we create. We ask the controller what state are you in, and based on the state, we update the controls and we get the ATM message from the view model. And then we can have these user interactions in this event structure. So when the card is inserted, we call the card inserted method here. And the UI here is just wiring everything up. So there's very little logic here in the UI. And in that way, there is very limited amount of testing for the UI, or through the UI, which needs to be done. We can instead test the controller and the view model and the database in isolation, basically. And yeah, to show you another case, here's the enter case where we need to enter an account number, press the enter button, and if it's found in the database, then we get through here and we call the user verified API call of the controller. Next, we need to start doing depositing and withdrawals. And going through the specifications, you see that we need to use the same user input and enter for doing that as well. And at this point, I decided to refactor a bit. So I actually moved the database from being here on the top level to being in the controller here. So now, instead of having the database on the top level, it's composed into the controller. So when we create the controller, we actually create a database within the constructor here. And then we can hide this logic where we query the database within this enter case here. So it makes the API a bit cleaner, and then we can have all the conditional stuff within this enter case later. And of course, we already have all the tests in place, so we can check, we can make sure that everything is still working as expected. So you might say, what about state machines? If you have taken LabVIEW courses directly in core 1, you start working with state machines, and I haven't seen many CLD solutions that hasn't a single state machine in them. So let's have a look first at what a state machine might be. So we have, typically in LabVIEW, we have a while loop with 2 shift registers. Commonly, it's kind of the canonical example from the core 1. And we have a state data, which we do some stuff with, and then we do a transition. And of course, there should be some logic, or there could be some logic deciding the transition or how it transitions then to the next state. But we could equally well use a class instead of a cluster. If we replace the cluster here with a class, we get some benefit of being able to protect how the data is accessed and hiding the actual how the data structure is laid out in LabVIEW within the class, and we can just have these methods for accessing the data instead. So it's a bit of an improvement, but we could take it one step further and put the state within the class as well. So make the state the class state aware, and then we can pull the state out of it, and based on the state we can then call a different case. Or we can decide to just have the whole conditional logic within the API of the class itself, and the class then manages its own state internally, and it doesn't really leak out to this top level VI which calls the class. And this is pretty much what I have done, but you see it's more or less equivalent to using a state machine. The main benefit, or the main reason why my designs tend to look like this to the down right and not to the top left is because the API containing the state is much easier to test, because we are not coupled to the top level PI with the inputs, the state inputs, and the cluster anymore. We can just exercise the class through its cycles, and it's less sensitive to changes to the definition of the data structure and the state, enum in this case. Cool. So let's go on. We have so often you read about changing requirements and how this is a big problem when developing a software. And in my experience, it's far more common that you rediscover the requirements, or you understand them better, or realize that it can't be solved in the way that you have tried to do, and then you need to change. And then it's a good thing that software is soft and we can easily mold it and shape it into a new form. So in this case, I hadn't read the requirements carefully before, but now when I came to the next state which I needed to handle, the ATM message actually needed to contain data from the database. For example, we need to show how much money is on the account in one of the states or one of the use cases. And of course, my view model does not know anything about the database, and I'm not really keen on introducing it to the database either, because it doesn't make sense to couple the view model to the database. It's pretty much a no-no from a design perspective. And I have my tests looking like this. So what I need to do is I need to refactor, and it's not that difficult to do. What we can do is just move the responsibility from the view model into the controller. So what I need to do is to update my test and have the method here belonging now to the controller class and not to the view model class. I can check that everything still works, and I can then integrate this one into my main VI. So it's a small change, but I felt pretty confident that I didn't mess it up, because I had my tests which were still passing after this change. But this is very common that I realized that this will not work, and I need to figure out some other way of doing it. And given that this is a toy example, you could probably solve it just by keeping everything in your head, but having this test scaffolding in place really helps in this kind of situations and minimizes the amount of mistakes. Another thing which makes testing difficult is when we have I/O in the system. In this case, we have a database, and we need to test making updates to the database at this point. So I decided to just use the actual database with test data, and this is because the implementation of the database is so simple that it doesn't make sense to mock it out or stub it with something else. So I did something like this. I create a temporary file, I add some test data to the temporary file, and then I can call my test methods on the controller, which now uses the temporary database. I have done a refactoring here between. Instead of feeding the file path into the controller, I now feed the dependency, the database that is directly to the controller. Yeah, I can start writing tests that look like this. For example, we can have a database containing this information. We have 2,000 in the account balance. We verify the user, and when it's verified, the account balance is fed into this verify user API call. So we fake it with some fake data here, and then we can initialize the deposition. We can enter $100 here, and then we can, after that, query the database for the balance, and we assert that it has increased from 2,000 to 2,100. So that is what this test tells. So this was pretty much everything that was to it. So I went back to my main VI and started putting it all together, and this is what the final main VI started to look like. And we have, if you start to look at it from a higher level, we have this leftmost part which just initializes the application. We register the controls on the front panel. We initialize the database connection and feed that into the controller to use as a dependent. We inject the dependency to the controller here. Then we can start reading the state of the controller, and based on the state, we update the ATM message, we update the controls, we read the left menu, and we read the right menu, which we output to the front panel. I'm not showing the test for these, but they're very similar to the view model tests I had. And then we can have this UI handling stuff on the right, where the user then interacts with the application through the buttons, and this calls the ATM messages. Not the message, sorry, the ATM controller API. And this design is very, to start with, in my mind, in my opinion at least, it's very clear. You can immediately see what's going on here, and there's not a lot going on really on the high level. Also, if you wanted to change now how we interact with the controller here, we could just replace this event structure with something that's hooked up to hardware, and we would just call the same API methods through the hardware buttons instead. And similarly, if we want to change the database to something real, we could just feed a real database in here in the beginning. So what fell out of this test-driven approach is pretty flexible in this case. So yeah, at this point I thought I was finished, and I hadn't actually run the application a single time through the main VI at this point. So I decided that's probably a good thing to do. And when I did, I discovered that there was some implicit requirements. So this may have been a bit of overconfidence on my side. I got to this point within about 3 hours. So I still had 1 hour left if you would do the exam to finish up. And we're able to finish well within time. But what I had missed was default values for the controls, or that the controls should remain in the states that they were put in an earlier state. And there was some initialization I had missed. For example, the left menu should not be empty. And if you are in the deposit state, for example, it should be something else. And my default case was just these empty strings. So I added a bit more tests to it, and then I was finished. But it was pretty easy at this point to just go test it by hand and add the tests one by one. Cool. So let's compare this to something that's not developed with TDD. So thankfully, NI provides the solutions to these exams, and we can have a look at what NI's example solution looks like. And given that this is such a small application, you could probably fit this in your head, and it's not that difficult to understand. But I would still argue that it's much more obscure than the solution I arrived at through using test-driven development. I have my quality measures about does it do what the user expect it to, and I assume it does because this is the provided solution. So in that way, it's not a bad solution. Is it easy to change? Well, I would argue that it's probably not very easy to change, and the reason is that there's no real clear separation of concern. Everything is just happening here in the UI BI, and everything is coupled very tightly to that. As I mentioned, the readability is not very clear here, at least not to me. You could argue that it fits in your head and you're able to reason about it. But my counter argument is that while this is true for this toy example, you probably couldn't fit a real big application in your head, or at least not a significant application. And even if you could, how long will it stay there? Will you be able to return to it in a week and still have it in your head? So for this reason, having a readable code is of course very important, but that should be kind of self-evident. So let's just quickly look at some statistics here. I'm almost running out of time. So yeah, about 4 hours to solve the exercise. I wrote 73 tests just by sticking at the process. It took about 2 seconds to run the tests. So they were, to be honest, a bit slow, but it was not really a problem here. 2 seconds is not that long when you to wait. If it gets to the tens of seconds, that's painful. And the reason I want it to be fast is, of course, because I run the test 100 times plus during the development here. There's a coverage analysis utility in LUnit, which I use to measure the code coverage. And this is maybe not the best metric to follow, but at least it gives you some kind of hint of how much of the code base is exercised by the test. And when you do the test first development, you tend to end up with close to 100% coverage. And during this development, I did virtually no debugging at all. When I made a mistake, it was during the green phase or the red phase of a test, getting from red to green. It didn't go to green. I made a mistake, which I needed to fix. But it was very easy because I was just focused on this one thing at a time. Okay, so let's just put this up there. So as I mentioned already, it's less stressful to use this compared to just whacking away coding. I get the confidence that my code works. I'm not afraid of changing it. It's a bit addictive to get the green light up. And my last point here is that it feels slow. And the reason why it feels slow is that it's kind of tedious to write these tests. And you feel like, yeah, I know how to do this. I can just solve it. But my experience is that it's actually much faster than not writing the tests. But it might be difficult to measure. Let's have a quick look at the architecture we ended up with. So we had a view model which knows about the controller, which calls the database. Then we have the main VI, which calls all of these. So it's not too bad an architecture all over, but we could simply refactor it to make it even better. We could make our controller call into an interface which would represent the database, and then we can have our implementation here, which calls the file, implement the database interface, and we could have the view model, and in this way we could separate the controller from the view model and the file. So we would have this core domain logic isolated from the rest of the system, and this means that the controller will not need to change if something below this boundary changes, and this is a very nice very nice feature of an architecture. We should try to protect the core of the application from changes to the details. I have 1 minute left, so let's quickly look at the APIs. So I ended up with 3 classes. They had APIs that look like this, and you might think that I just hidden a lot of the ugly stuff behind the APIs, but I would actually argue that no, not really, because when you do the test-driven stuff, you try to do the solution as simple as possible, and the actual block diagrams tend to look something like this. There's not a lot to it, and The only one that has a lot of or some logic is the enter case, where we need to do something differently depending on the state of the ATM. But even there, it's quite clear from the block diagram what it does. And the code is available on GitHub. You can go look at it on your own. So yeah, I'm running out of time here. This is my last slide. I would suggest that if you're interested in learning more about this, it requires practice, and solving toy examples like this is a good way of practicing. If you are able to pair with someone who has experience of working with test-driven development, that is a great way of learning, because you can avoid a lot of these mistakes that you might do early on. And at least to start, I think it's good to just religiously follow the discipline, because and then when you get more experience, you can move away from it at some point. If you want to have more material, I did, as I mentioned, a presentation during GDevCon. It's now on YouTube if you want to go look at that one. I also did a Snake game where I do the coding live, basically. I developed the game of Snake using test-driven development. And if you haven't seen the workflow before, then this is kind of a nice demonstration of that. And it's pretty much writing it test by test until we have the full game in the end. But that's pretty much all from me. Thanks for joining. And if you have any questions, feel free to post them. Yeah, thanks to you for listening as well. Cheers. So yeah, as there seems to be no questions, maybe we can round off here. And if you want to discuss more, just reach out. You can find me on in this event. There's probably some kind of direct messaging feature. I'm on LinkedIn. You can find me there, and then of course you can through my business find contact information as well. So just feel free to reach out to discuss more. I'm very passionate about this topic, and be cool to change some experiences with you all. So yeah, thanks a lot for joining this session, and have a nice rest of the conference.